So in this topic, I'd like to introduce us to vectors and maybe how we can think about them in relation to more classical concepts in geometry that one could argue it kind of evolved from those. I mean, maybe that's not the exact mathematical history, but there's definitely kind of an evolution of concepts here. And let me start off by looking at a line. So like if I redraw the line that I've got pictured there, I've drawn it with kind of two arrows. And what I take that to mean is this line has no endpoints. And that in classical Euclidean geometry, that's the way we define it. It has no endpoints. So in that sense, if you ask like, what's the length of that line? The answer is because it has no endpoints, it's infinitely long. And if I were to use it in physics and say, well, what's the magnitude of whatever it's describing, whether that's a velocity or an acceleration or maybe even a force we're going to use, we're going to want to describe those, and they're going to need to have like a direction, but they're also going to have a magnitude. And the answer is with a line, you can't really do that. And direction is problematic as well, because if I said, hey, maybe this represents a force, like a push or a pull, but is it a push or is it a pull? Because the arrows point both directions, so there's a lot of ambiguity. So that makes it kind of inconvenient for physics, and that was even true way back in like Isaac Newton's time. Lines were definitely there, but he tended to use line segments a lot more, and rays have also been used kind of in the classical history of physics. And Ptolemy, the ancient astronomer in particular, used the ray as a geometric object as part of his technique. So let's look at the ray next here. I'm not going to spend a lot of time talking about Ptolemy and how he used them. But what is a ray and why have I drawn it this way? Well, it's basically defined by a point, and then it propagates in some direction. And in that sense, I've pointed with an arrow in some direction here. But similar to the line, it is unbounded in that other direction. So what contrasts it from the line is it does sort of have a bound on one side, or a point that it starts from. But other than that, it is unbounded going in one direction. So I'd like to maybe write over here to the side and say I can definitely associate with the ray the property that it has a direction. That's potentially good for describing things in physics that need to have direction as one of their properties. But the limitation is it's hard to assign a magnitude to a ray. So that rays in that sense, it's limited how you might be able to use them then. And then if we look at the line segment, so the line segment in classical geometry is defined by 2 points. And Isaac Newton used this a lot, and it was really well established at that time, like how you would refer to a line segment based on the 2 points that were there. So it was something that had some of the properties, because like if you look at this, like what property does it have? It definitely has a well-defined magnitude, unlike the line and the ray that are in some sense or entirely unbounded. The line segment does have bounds because it's defined by these 2 points. But it doesn't really have direction in as good a way as a ray does. So it's maybe lacking in that department, similar to how a line is lacking that characteristic. But it still kind of worked. Like Isaac Newton used it because it does have an orientation that's well defined, and I think he just used language to kind of describe how a line segment would be related to something like an acceleration or a force, because that's a lot of what Newton was focusing on to try to describe motion as we observe it in reality. But what's better about a vector? Well, again, using the rules of classical geometry, which are really well founded with a very good mathematical basis, you had to refer to these 2 points if you're using line segments. If you drew another line segment somewhere else with the same orientation, you had to define different points. And so in that sense, you couldn't move it around. And it turned out it was later argued in like, I think the later 19th century, somewhere around there, was when vectors really took hold in physics. And the argument is like, it stifles us to have to be using these tools that are associated with definite positions in space. Let's use this other tool that at that point math had defined a new thing called a vector. And the cool thing about vectors is their definition is not tied to a particular location in space. And if you ask what is a vector, I don't know if I can really answer that in this class. That may be an advanced math class question, but vectors are well-defined mathematical objects, and as a physicist, I just know how to manipulate it and use it for problem solving, and that it has the right properties. So look in the math book for some better definitions. But the key thing is that it can be moved around. It's not associated. Really, in that sense, a very simple way of saying what what does a vector have? Is it has magnitude and direction. And again, if you do look up the mathematical definition, you'll find a lot of talk about the different mathematical properties that vectors have in terms of how you manipulate them. That's kind of a math first approach. But I'm taking a more concepts first approach to vectors and saying the concept behind a vector is it is really only associated with its magnitude and direction, gives up this association with position that these other three classical geometric objects had, and in that way winds up being a lot more useful in physics.